Great. Okay, so thanks a lot. Thanks everybody for coming. It's great to be giving a second talk at JuliaCon. So today I'm going to talk about JSO Suite. This is mostly a work by Tanguy Migaud, uh, who could not be here because he's on the other way. He will be at the Jump Dev conference, so if you're going to that, please talk to him. Uh, and the slides you can find in the QR code. So JSO Suite is part of the Julia Smooth Optimizers packages. So JSO stands for Julia Smooth Optimizers. I will use that a lot. And I just want to show the main takeaways if you need to leave early or hungry for any reason, or if you just want to see this slide. So JSO Suite is a nonlinear optimization interface, which means it's like I want to optimize things. I just want to get the user-friendly thing, right? It's backed by Julia Smooth Optimizer, so we have developed a few packages over the years. Julia Smooth Optimizer was created in 2015. It is mainly research focused, so we have worked in a lot of packages for cutting edge solvers, and now we are looking a little bit for the user friendliness. And the main idea of JSO Suite is that you have a single package that you load using JSO Suite, and you have the solver selected automatically based on what you have. So you just create your problem in the simplest way. You just give the objective function, and it works. It will use what is loaded. So if you have more packages for optimization, IPOpt being the most famous one, you can use that as well. And we are looking for enthusiasts in this field. So most of the development in JSO is based on research. So user friendliness is not something that we are really proficient. So if you're interested in just helping out to give your opinion, or even just I know how to make things better, or if you're just interested in optimization in general, please get in touch with us. Help us make JSO better. Okay, so Julia Smooth Optimizers, you can find us at jso.dev. It's this organization since 2015. We started all of this when we decided to streamline optimization solver development, which essentially means you're doing PhD in optimization solver development. And when you normally have to do that, you have to worry about where are things coming from. So you have an optimization problem that's coming from somewhere. For instance, pretty common situation. You just have your advisor giving you a file saying, this is our objective function, which was not great. And then you do that, and after a while you say, okay, now I'm going to publish this software, and then, okay, now you have to install this Fortran package that exists since 1990, and it needs a lot of dependencies, so good luck. So you're not really prepared for that. So we're like helping you go from, I just want to work on the solver, so give me the problems, I don't care where they come from, do the thing, here's the output, and generate things nicely. So we talk more about this in other talks, in other JuliaCons and Jump Dev, so you can find more information about all of that. And since optimization is essentially linear algebra and multivariate calculus, we have a lot of packages on those things, either in conjunction with optimization or by itself. So these are our 6 most famous packages in number of stars. One of them, the most starred one, is Krylov.jl, which is for linear algebra. So it's standalone package, doesn't depend on any optimization thing. And it's pretty well used out there, even by indirectly by SciML. So you possibly use that if you use differential equation solver. And we had a strong research focus. We have a strong research focus. I'm a research software engineer now in some other field. But the Julia Smooth Optimizers is driven by research, so there are a lot of developments going on. For instance, now we're talking about non-smooth optimization and things using GPU. So if you want to get involved, please check jso.dev. And of course, none of this would be possible without the many contributions that we had over the year. So thanks a lot for all the contributors. Like so many people to count, probably not too many to count, but so many people. Thanks. Just stay a while here just to say thanks to all of you. Specifically, JSO Suite now. So the way that JSO solvers work is you have a model or a problem, depending on the field that you come from, and then you give this model to the solver, and then that solver gives you back an execution stats. So the provenance of this model or problem is varied. So sometimes you are in the industry and you have AMPL being used. Sometimes you're just an academic doing benchmarks and you have QTIS. So it can be from many places. Or you can just use AD and give a function. So that's why we separated this. So you don't have to worry about model when you're doing your solving. On the other hand, if you just want to solve your problem, you don't want to care too much about the solver. So that's where JSO Suite is coming in. So a model in our field is an optimization problem like this. You want to minimize a nonlinear function. You have nonlinear constraints, sometimes also bounds on your variables. And what you need to make this solvable in our field is derivatives. So you at least want some first order derivatives, but the really good stuff uses second order as well, right? So you want some IP-opt, you need the Hessian. So as I mentioned, we are doing this for a long time. So if you want to create an optimization problem right now using one of our packages, you have a lot of options, right? And that's a lot. Like if you want to say to someone, hey, you want to work with us? Here's 50 packages for you to learn, right? But the idea being that there are many ways to create an optimization problem using JSO. And there are many solvers to choose from. Some of these are just wrappers. Some are pure Julia implementations of pretty good nonlinear optimization solvers. And also, there is a linear algebra ecosystem that is not going to be in this talk. But, I mean, we have to give some love to that ecosystem. So where does JSO Suite comes in all of this? Well, JSO Suite is essentially wrapping this part and make it a bit more user-friendly. So instead of worrying specifically about the model provenance and specifically about the solver that you're using, we try to make it easy for you, and we focus on a function called minimize. So minimize in yellow here is JSO Suite. The problem is something from somewhere. We're going to go over some examples, and you just have an output. Optionally, you can give the solver as well, and then you can be precise on your solver requirements. So a few examples on how to use JSO Suite. The first one, the simplest example, many people want to solve this, minimize a function. So I'm going to try to give some motivation for the non-optimizers in the crowd. You have logistic regression, for instance. And this is essentially, I want to find this nice red curve that's going to help me classify the points, separating the 0 ones from the 1. And that is an unconstrained optimization problem. Essentially, you want to minimize a function. So if you have that function, you can just say minimize f. If you give a starting point, things go better. That's a normal rule in the field. So this is the example for that code. So you can see it's not a lot of code to make that work. A lot of Julia things going on. So this is a sigmoid function using if-else. I define the cross-entropy loss, the classifier thing. And this is the objective function, fit obj. So this is the fit method from the classifier. Here I'm just saying it's a sum of the cross-entropy loss. No, the details don't matter. This last part is the fun stuff. You can just say minimize fit obj. Starting point is once, why not? And it works, right? So first example. If you want, you can give the solver. So right now the interface is you give the name of the solver as we have it internally. So if you give the IP-opt, it will use the IP-opt solver for this problem, which is overkill. If you don't use IP-opt, so the normal solver that we have for this is our own implementation of LBF.js. It's a pure Julia implementation. So it handles multiple precision, for instance, right? Another example of nonlinear optimization problem, and we can showcase the largest interface, is a portfolio selection. So you have many stocks and you have money, great for you, by the way, and you want to decide how to invest your money on this portfolio. So 50% on NVIDIA and another 50% on Bitcoin, right? Why not? So this is an optimization problem. In this case, I'm thinking about the Markowitz model, but the main idea is that you have an objective. In this case, you want to minimize your risk while also maximizing your profit. So it's a balance between two things. You have bounds for these values because you're essentially saying how much are you putting in each stock. So it's between 0 and 1. And you have a constraint, which is a function, this constraint and their bounds, which is I'm going to take all of these fractions. It must add up to 1, right? So this is the normal interface for that. And this is the implementation of that problem. So you have the the mean and variance, the covariance matrices, and you define this Markey function, which is the Markowitz minimization of the risk, and with some term for the maximization of the returns. But essentially what I want to say is it's functions, and you just give the functions in that order to minimize, and it works. So in this case, since it's a constraint problem, we are using Percival, which is another one of our solvers. One particular thing that people coming from MATLAB ask me a lot is I want to use quadprog. So if you know quadprog, you already had the spoilers for this slide. But the idea being that, well, in that particular case for Markowitz, that is a quadratic problem. So it's specifically the function is quadratic like this, and the constraints can be expressed as a matrix times a vector. So they are linear. So I don't want to actually give a function. I want to just give the values, matrices and vectors. So you also have that interface here for minimize. So minimize and then these things, and it also works. And that's the same example again if you want to copy paste it later from the slides. In that sense, we also extend, so one of the things that we'll study for a bit are nonlinear least squares. So essentially trying to fit a nonlinear function, if you want to think about machine learning. The idea here is that the objective function in this case is the norm of a multi-value function, which you can think about, you can think of as the residual of a problem. So you have the errors of your fitting, okay? So this is essentially minimizing, doing nonlinear regression, trying to minimize the distance for each one of these equations separately. To minimize a problem like this, you can just say, here is my residual function, and you have to inform the number of equations. And this is an example of that. So this is a nonlinear fit. These are all fake values. Don't have any good example ready. So these are fake values. So this is a completely nonlinear model. And it's pretty short to do that. So here is the nonlinear function that is used to fit that stuff. And you can just define your equations using the vector notation in Julia. And it's also just works. Again, this is being solved by JSO solvers internally using one pure Julia implementation of, I think in this case might be a Newton method, second order method. Finally, maybe not finally, but you also have the option of actually using the full abstract NLP model from JSO. So if you do say, I don't want the easy stuff, I don't want just autodiff, I want to control completely how my model behaves. Or for instance, you're doing something with PDE constraint optimization, so you want to use another package of ours, the PDE constraint optimizers, I guess, and then you want to take that, create our optimization problem, and just give to minimize. That also works. Okay, so it's still possible to use the rest of the models, not just the automatic differentiating ones. So one example that for PhD students is pretty relevant is the qtest model. So when you want to do benchmarking, you have this package called qtest. It exists for some years now in one way or another, and we used it to create benchmarks. It has maybe 1,500 problems by now, and it's all Fortran. So this is essentially taking that Fortran code, compiling it, and giving it to you. So if you want to do benchmarking with this, I think has millions of variables in some of them, and you can do benchmarking with that. So it's easy to just go there. And one cool thing that we are hoping to get to all of our packages, but the main ones already accept, are the options that you give to minimize. So the options are essentially passed to the solver that you use internally. So most of the solvers, the most famous ones, will have these arguments. So atol and rtol for the absolute and relative tolerance. But the cool stuff here is the callback. So if you have the callback function, we're going to call it internally in some of our solvers. And this is an example. This is logistic regression in 2 dimensions with a quadratic function. And I have a callback function here that I have cut because plotting is hard. And it essentially is a function that receives the 3 things that you care about: the model, the solver, and the output. And then you do stuff with it. In this case, I plot and save in a frame of the animation. So I can actually see how my optimization model is working to minimize this problem and to find the logistic regression bound. So this is a simple example, but you can do that, for instance, to control the loss of your machine learning model, for instance, right? Most of all, it's just cool to do as well. So JSO Suite is essentially trying to make your life a little bit easier. So it's user friendliness first. We have shown a few examples where you can just take our various model sources, and you can use many of the optimization solvers, and you just plug those things there, and it works, right? So that's the takeaway of what JSO Suite is for. You can just use it if you want to minimize things, and you don't care so much about like what's going to be used internally. So essentially, if you're an end user and just want to try something fast, so first prototype, you can start with JSO Suite. And that's why we are calling JSO Suite our one-stop solution for optimization. So I hope it helps get more people involved with JSO. If you want to get involved, so our main communication channels are, go check the website. There are some tutorials there. There are news as well when things change, and the communication channels that you can find us with updates will be there. The short version is that we are on the Slack and on Zulip, mostly on the math optimization channel and some other places. And you can find us in the GitHub discussions for JSO. And you can also check my GitHub, my YouTube, Abel Siqueira, like and subscribe. But that's because there are some tutorials in the YouTube as well if you want to get involved in optimization. And that's it for me, so thanks a lot for listening.
Yes, thank you, Abel. Any questions? Yes, quite a few. That gentleman first, and you will be the second. Yeah.
Yes, sorry. You might have covered this, but I just wanted to confirm that it supports nonlinear constraints as well, right?
Oh, yeah. Yeah, that's the main use case.
Yeah. So the main use case, yeah. Okay. And also, do you have like alternative optimization algorithms? For example, I saw you had BFGS, right? But do you also have, like, example, polyop that alternates between Atom and BFGS?
Which one you said, sorry?
Polyop. There's like
oh, yeah, okay. Well, we don't have that one. We have many optimization solvers. So the pure Julia ones that we created, we have. We have wrappers for IPOpt. We have a wrapper for Nitro. And we have now a way to communicate with Jump. So if Jump has it, we can use something to use it. It should be easy. So that it should be easy. Should. to also create a new wrapper to use existing solvers. But we are not working on that intensely. So if you want to get involved to do that, we help you get that done.
All right. Oh, and then finally, is it easy to convert objective function from like what's it called, differential equations that you let's say you've written one in a symbolic notation and use that for your module?
I'm not sure because it does depend on what they do internally, but there is some intersection on how we do things. So for instance, our AD NLP models uses a lot of different backends. So AD NLP models being the thing that computes the automatic differentiation. So I think right now we are using a package by Guillaume, which is sparse connectivity something. I don't remember the name, but it's doing the AD like that. But for instance, we had some investigation with Zygote at some point. So there is some intersection. So I imagine it shouldn't be too hard to connect the two of them.
Okay, thank you.
One, two. So thank you for the talk. Can this support non-differentiable problems and global optimization and so on?
So a great question. So on the non-differentiability, so it is Julia is smooth optimizers, but actually there is some work being done right now. So the other creator, Dominique Orban, he is now working with non-smooth optimization. So it might be possible to do something like that. I have zero knowledge of non-smooth, so I don't know. But there are packages, so you can look into that. And on global optimization, nothing. Nothing currently because it's mostly the idea of being you want to look for a first order optimization, first order point, right? So we don't look so much for the anything that can be provable global, or we don't have multi-start. Multi-start should be possible to implement, but we don't have it implemented. And on other kinds of global optimization like convexity, we are not touching that at all. Thank you. Yes, the question was, have you tested the scale of the problem and the scalability? Kinda, yes. It does depend on which solver, but the Q-test benchmarking includes problems up to millions of variables. I think some of our solvers will struggle with some of the largest ones because they are really large, but also my computer struggles with just loading them, so I can't really benchmark. But yeah, we have tested a few things. The IPOpt solver at least handles those very well. And we are looking for people interested in working into improving some of our solvers as well. That's something.
More question?
Thank you again, Abel,
Thank you.
for the speech. And we will have a launch session at third level. And if you have any questions, all the lecturers and speakers are there. You can meet them and catch them, ask questions there as well, if you're interested. Thank you again, and thank you again.
Thank you.